Hi, good morning. Welcome, everybody. Welcome to our event. It's the second edition of the ICMC workshop on recent advances in computational mechanics for industry. It's an event that we are trying to establish a tradition here in the ICMC. And the first edition of the event was in 2024. By that time, we took the time to make a homage to Gustavo Buscaglia. It was a very nice event. We had many friends of Gustavo and many very good researchers here, and it was a very nice event. So this time, we thought that would be good to make a homage to Professor José Alberto Cuminato, that everybody knows as Poti, right? And in the occasion of his 70th birthday, it was very convenient in that way. So, and I want to welcome everybody. I hope that everybody is set. If you need something, just tell me, right? I want to start saying some words about our Professor José Alberto Cuminato, and afterwards I will tell something more practical about the event, and then we can start with the presentations, right? So, well. Everybody knows already why he's called Poti, right? But for those who doesn't know yet, he comes from Potirendaba. It's a small city. It's located here, right? And it's somewhat near to São Carlos. Yeah? It's near to São José do Rio Preto, right? It's a small city. It's 18,000 inhabitants by now. And São Carlos is about 266,000, right? So it's a very small city. And yeah, and Poti, he did his undergrad studies in the São José do Rio Preto in Unesp, and then came to São Carlos in 81. I hope that I'm getting the dates right. 78. All right. So sorry. to do his master's degree, right? And then he went off in 81, right? Off to Oxford to do. He did 1 year master's and then his PhD over there, right? Well, everybody knows how important Poti is for the development of the applied mathematics here in Brazil and in the world. And then, since we're living in a times of artificial intelligence, I asked some artificial intelligence to do like a time track of the contributions of Poti. And then I got something like this. This was from Notebook LM. Was a very nice picture. Here are the foundations of these buildings over here, and the foundations are academic roots in Brazil, the course in mathematics, the PhD in Oxford in 87, and achieving this livre docência, what's habilitation, if you want, in 1990. And then over here on the contributions that he did while becoming full professor, he served as director of ICMC, and he also was over here. He was president of the Brazilian Society of Applied Mathematics, Computational Applied Mathematics, what is SBMAC. So the AI mistake here, S for 5. And yeah, and he had many honors, and one of them was named Fellow of the Royal Society of Edinburgh, and also coordinated the SEMI. But I thought that was missing some parts here. I tried again a second iteration, and I got this. It was a very nice road. starting with his PhD. Actually, the road we should follow this way, but the next step is over here. And this is why I put this picture here, because one of the most important things that he did here was found the computational fluid dynamics group that was in '93, and the group that I'm part from, and that I came here to do my master's degree and PhD. By that time, it was oh, no, not '93. It wasn't 2000, but it was because he created this group here. He and Murilo and Valdemir and other colleagues in that time. And then we move here in 2000, when I came here to study, to do my master's. He became full professor. And then he, over here, he served as president of the SBMAC, Society of Brazilian Society of Computational Applied Mathematics, and as director of this institute in these times here. The director was 6 to 10, and the SBMAC was from 5 to 9, I guess. And this is perhaps the next step in his career was, I guess, is the most important thing, that the most impactful thing that he did here in this institute. That was the creation, the foundation of the CMI. It's the Center for Mathematical Science Applied to Industry. And it was a big funding from FAPESP, about 50 million or so of reais, and allowed many things, not only bring money to this institute, like institutional money from FAPESP, and also money that allows us to establish here the supercomputing center that we have here with the Euler supercomputer that is above our heads right now. By the way, this auditorium here was built in his time as director of ICMC. Am I right? Is that right? I think so, right? Yeah. And the Euler is above our heads right now, somewhere around there, yes. And right, so this was not only by the funding and etc., but also he established by that time a culture that we didn't have here before, that was to do those study groups and to bring applications to industry, to production sector, and etc. And we started with CMI to do this yearly, these study groups with the industry. Was a very nice event that happens every year. So the last one happened this year in Salvador, and it was something that really left a mark in the applied mathematics scenario here in Brazil, right? And then end up with this prestigious academic nominations. These logos are all wrong, these things of AI, but I did fix it right here. He was nominated International Fellow of the Royal Society of Edinburgh, since Sean told me how to pronounce that correctly. It was in 2012, and he was nominated also for the Brazilian Academy of Science in 2014, and also he served as a treasurer of the ICAN, the International Council of Industrial and Applied Mathematics, and right now he's the editor-in-chief of Dianoia, is a newsletter kind of the ICAN, right? So these international recognitions tell a lot about the global impact that he had in numerical analysis, and also could be picked up by this artificial intelligence. And this a little bit more about the CMI. I told a little bit already, but this is something that was really important, and I made this this thing here to show that things that CMI promote, like the applications in manufacturing engineering, applications in public health and government, and also corporate education, and one of those being this We have a master's degree right now, thanks to that. We have MBAs and these study groups with the industry that are very, very good. So these LLMs can tell a lot about POT, but there are some things that these LLMs cannot tell about POT, right? And what are those? Things that I learned in this 25, 26 years of living, being here with him and every day dealing with him. His dedication and commitment to scientific development. It's unquestionable, right? He has a strong institutional thinking. Everything that he did, every decision that he made was thinking about the institution. That is very important. He's something that he does a lot. He has unbreakable moral and sense of justice, and this is something that you perceive by dealing with him day-to-day basis, and unquestionable honesty and integrity, and also transparency. These are things that no LLM can tell you about POT, right? So this is why we're doing this homage to him. I'm very proud of this, and I'm very thankful of his leadership that he did up to now with our group and applied mathematics in Brazil. So thank you. I hope that you don't laugh a lot about these pictures, but something about our history here with Sean and Murilo in 2004, and here was the book that he published with Messias, and over here in Japan with Michael, and over here was this year in Chile, and over here he was Sheikh in Dubai. All right. So thank you, and welcome everybody. I hope you'll have a great time here. Thank you. Let me say some things about the practical things about the event. I want to thank first the ICMC for hosting it, the CMI for helping me organizing it, and the Dean Office of Research and Innovation that also got some funding, and also funding from FAPESP. I want to thank the staff here at the university from Event, Marília, Fernando, and Reinaldo. Thank you very much. I want to thank the Escritório de Grandes Projetos that helped me a lot, Fernanda, Luan, and also the staff from audiovisual staff, Paulinho, thank you very much, and all the people involved. That was a lot of effort to bring this to happen, right? Thank you very much. Thank you a lot. This is the program. You all have the program. This is the link for the program if you want to just take a picture here to save the QR code. So we'll start a little bit. We are a little bit late already, but I'm about to finish. And today, about something about the poster sections. We are arranging the places to hang the posters. By the time of the coffee, we will have already the places there. So you go there, hang the posters, and you'll be ready for the presentation. I have 16 registered, so should be enough, I guess. Presenters should be ready at the coffee breaks, right? So to answer questions and etc. It's a quite long coffee break. It's about 40 minutes, so it's enough. And participants can later get a ballot that will be available with Marília in the beginning, in the entrance. And with that ballot, you can vote for the best poster award. At the end of the event, we will award the best poster with a prize, right? And please vote before tomorrow lunchtime, so we have time to do the counting. It's a lot of people here. So, and today we have a conference dinner. Actually, the dinner is in a restaurant called Tasca Manjerico. It's a Portuguese restaurant. Please, if you want to go, I ask you to go to this QR code. We'll also put the link in the website, and then please go there and register. We have only 40 seats available. The restaurant is small, it's not very large. So we will take the first 40 subscriptions, and then we will we'll keep it with that. Sorry for that. The restaurant is very nice, but it's quite small. It's pay on site. Is a la carte menu. The menu is on this form, so you can take a look beforehand. And details and location are also in this form, right? And all right, that's it. Thank you very much again, and let's start with our event. The first speaker that we have today is a great honor to introduce to you. Is a very good friend. You saw from the pictures there that we are friends for quite a long time already, right, Sean? And he was professor at the University of Oxford when he was supervisor of Poti, when he did his PhD over there. And afterwards, he moved to the University of Strathclyde, where he's right now professor, retired professor, but not so much retired, right? All right. He is also fellow of the Royal Society of Edinburgh, right? So very good honor. And also he received the ICMC Medal of Honor here in our university. And also similar Medal of Honor in the State University of São Paulo, Unesp, right? So he has awarded lots of honors here in Brazil for his contributions to the Brazilian applied mathematics. And he will be nominated actually as a fellow of the Brazilian Academy of Science also. So it's a great pleasure to introduce you, Professor Shamaki. Thank you very much for coming. Thank you. You're using this?
You're going to use the microphone. You want to use the headset?
Yes, this is better, I think.
You want to use the headset? Or?
You don't want to use the headset.
I think this is fine. Yeah.
Okay,
Yeah.
I'm just...
I need this, of course. Let's just check this. There. No, how does it work? No,
Let me see. No, it's done on.
that's it on.
That's it.
And these two come. Good morning. Primamente, eu gostaria de agradecer a Fabrício por me convidar. It's greatly appreciated. I'm very glad and very happy to be here after 7 years, long time. Now, my talk, I'm afraid, appears to have nothing to do with the title of this meeting. And I apologize for that. I think Fabrizio perhaps was too polite to tell me to change my talk. I sent it to him a long time ago before I realized the actual title. But I have a sort of excuse because it's Potty's 70th birthday. He's a young man, but he may not think he's a young man. He may even feel a little old. And I thought it'd be rather nice to talk about his childhood and his school days when he was studying geometry. So this is what this is about. It's just Euclidean geometry. But it's Euclidean geometry that eluded Euclid, and indeed the ancient Greeks. So it's a wee bit different. It's an amalgam, in fact, of 5 articles that I've just recently written. More scholarship than research, I would say, although there's some originality in it. So, start with Pythagoras' theorem. I'm sure you've all seen this. There are many proofs, of course, of Pythagoras, but this is, well, probably the simplest. Simply saying that the big square, the area of the big square is equal to the area of the red square plus the 4 congruent triangles. And of course, you do some first-year algebra, and you find you get Pythagoras' theorem. Okay. Sorry. Well, another interpretation, of course, is that the red square there, or the area of the red square, has to equal the area of the 2 blue squares combined. And it was that reminded me, or at least I didn't know it, but Euclid's own proof is rather subtle. And I think it's worth just demonstrating it. Excuse me. The idea is that what I've done is I've removed one of the squares. I'm just going to concentrate on the small square. The small square, the area is obviously, or the area of the triangle, the red triangle on the top left, is obviously half the area of the square. And what we do is, because the area of a triangle is half base times height, you just slide that down. I can do it. You slide that down to here. That triangle has the same area as that one. Then the clever thing, you flip this. Well, you don't really. This is a congruent triangle. The 2 sides, and that angle, of course, is equal to that. Easy to show. And then you slide this down, and you get this. So now you've found that the area of that triangle is the same as the area of that triangle, and therefore the area of that square is equal to the area of that rectangle. And then you go ahead and you do the same thing here, and that was Euclid's original proof. And I like it. I think it's very subtle. Okay. Carnot's theorem. You may not have heard of Carnot's theorem. It says that if I take any triangle here, and the sides are A, B, and C, and I divide them up in the following way, I choose a point P. That point can be anywhere inside the triangle. And remember, it's an arbitrary triangle, not a right angle triangle. Oh, I'm so sorry. Scoopy. Sorry. I haven't given a talk for 7 years, so I'm a bit out of practice. We take any point here, we drop perpendiculars. And then the easy way to prove this is just drop join up P, A, P, C, and PB. You get 6 right angle triangles. Use Pythagoras, and that just drops out here, that result. Now, I claim in a way that this is a generalization of Pythagoras, because if I take this point here and move it over here so that we have a right angle, and then I pull P along into C, like so, we have a right angle here, and then P we take up to C, we get this, and that gives us that expression below, which of course is Pythagoras. Okay, well, it's somewhat unsatisfactory to use Pythagoras to prove Carnot's theorem, but could we use Euclid's idea? Because Carnot's theorem is simply saying that the sum of the areas of the red squares are equal to the sum of the areas of the blue squares. So can we use Euclid's idea? I don't think anyone's done that. So if you're really bored with the talk, you can spend your time trying to work that out. I haven't thought about it with any depth. This is Carnot. He was actually Napoleon's general. And some history, Lazare Nicolas Marguerite Carnot, he was a French politician, military engineer, and a mathematician, obviously, who played a key role in the French Revolution. And he oversaw the organization of the army, significantly expanding it through conscription. And he became known as the organizer of victory, which I'm sure sounds much better in French. Anyway, he after Waterloo, when Napoleon was defeated, he had to go into exile and died at the age of 70. Well, more about Carnot's theorem later on. This is what I call running around in circles. We have 3 circles here, and they're all the same. They're congruent circles, if you like. Let's say their radius is r. And the question is, they all meet at one point here, Q. And if they meet at one point, then clearly there are 3 other points where they meet, P1, P2, and P3. And this is their circles, their centers, C1, C2, and C3. And if we draw a circle around C1, if we draw a circle with center Q around C1, C2, and C3, then clearly that circle will be the same as these original circles. But the question is, what about the dotted circle, the circle that goes through P1, P2, and P3? Is that also identical with these? Well, it turns out it is, and the proof is interesting in that it requires just the concepts of a rhombus and a parallelogram. We see here, we create these rhombus or rhombi. That there is r, the radius of these circles. That's also r. So is that, and so is that. So that's a rhombus. And so is this a rhombus, but the same argument. So you know that this here is both parallel and the same length as this, of course, which is the same parallel and the same length as this. And then what we do is we draw a parallelogram. We join C1 and C2 and P1 and P2. And that is the red figure here. And what we've then proved is that that line there is the same length as that line there. And we do this 3 times. We form, again, a rhombus here and a rhombus here. And then what we do is we form the parallelogram. And here it is here. All right. Now we know that that side now is the same as that side. And finally, we work out, here's a rhombus, here's another rhombus. So we've got that there is equal to that and parallel to it. We form again the parallelogram, the red figure here. And we've now shown that this side is equal to that side. So, it's a rather complicated diagram, but basically what we have is the red triangle here and the blue triangle here. Now the red triangle here is circumscribed by this circle, which I call C. It contains C2, C3, and C1. And remember that that circle we'd shown was identical or congruent with the original circles. But this triangle here, of course, is congruent with the blue triangle. And it is circumscribed by the dotted line, this circle. So that proves then that the dotted circle there is identical with the other circles. Okay, I just include that because it was such a simple idea, just using rhombi and parallelograms. So that's really what I've said there. I'll not read that out, but this is often known as the Johnson circle theorem. And the proof that he wrote was 8 lines, very, very short. And that's what, well, led me to write out a simpler pictorial proof, which I've just given you. Well, one last thing. If we have 3 identical circles, and if they don't join just at one point, but they meet at several points, they'll meet obviously at 6 points, and here they are here, and that forms what we call a triquetra. And that's very common in heraldry, and the Celtic. You see it in crosses in Scotland, actually. And a chap called Mackenzie actually studied this, and he was able to show that there are many circles here, and he was able to show that all these circles, the radius of them, was related to the original circle. But it was a complicated expression and not really worth, not very elegant. So I don't mention it. Here's a problem. I've got a circle, we'll call it the unit circle, and I circumscribe it with a triangle, circumscribe that with a circle, circumscribe that with a square, and so on. Pentagon and hexagon and so on. And the question is the radius of the eventual circle, is it bounded or unbounded? Not just clear. And if it is bounded, how big is it? Is it the size of the universe? Or indeed, is it really quite small? You make a guess, perhaps, at what you think it should be. If it is bounded, that is. We start with an easier problem, which is the triangle, an equilateral triangle, circumscribed by circles and another triangle and so on. And we ask the question, is that bounded? Well, it's quite simple to see that it's not bounded. We look at, again, we're just going to Pythagoras. We're looking at this ADC, and that gives rise to that. Perhaps what I should say here is that R2 is going to be the radius of this circle, the inner circle. R3 is going to be the radius of the red circle. And the difference between the two will be D2 here. And the distance down here is L. I think L3, I've called it, yes. So we look at, first of all, as I say, this triangle, and then we look at this triangle here. We write the two together. We eliminate L3, we end up with a quadratic equation, which we can solve. We neglect the negative root, and we see that D2 is R2, but R3 is defined to be R2 plus D3, and therefore 2R2. And if we take R2 to be 1, i.e. the unit circle, we simply get that Rn grows like 2 to the n minus 2, so it's exponential growth. So it's unbounded, this problem. If we look at the more general problem of an n-gon circumscribing circles as n tends to infinity, then what we have here is two circles. Here's the Rn minus 1 circle, the blue one, and here is the Rn circle, the red one. The difference between the two being dn. So we have here Rn minus 1 plus dn is the radius from 0 to c. And it's trivial to show that the angle here is it's 2 pi over n. There's n segments, and it's 2 pi, so you divide one the other. So what we do is I'm sorry. Oh, dear, I'm so sorry. Here we are. What we do is here, this is a right-angled triangle. So this triangle here, again, is just Pythagoras, which is this term here. And this one is the old-fashioned thing that you learned at school, probably in your first year. You know, a squared equals b squared plus c squared minus 2bc cos a. You apply that, and you get this here. Again, you eliminate ln in this case. Ln is that distance. And you get eventually this, a quadratic. And when you solve that quadratic, you get this here. dn is equal to that, but we know Rn is Rn minus 1 plus dn, so that cancels out, and we're just left with Rn sec pi n. So if R2 is 1, we find that Rn can be expressed like this. It's a product of sec pi over n. But we still don't know, really, whether that's bounded or not. I don't think it's immediately obvious. So, back to undergraduate stuff again. We simply take logarithms, and then we need only show that that is, tends to a non-zero constant. what we're doing here is we're comparing it's now a series rather than a sequence, and we're comparing that one term with a comparison theorem, usual second year undergraduate stuff. Choose x equal 1 over n, and then look at this limit. And the limit comes out to be that after using L'Hopital's rule twice. Okay. So what we find then is that this is indeed bounded, so we'll just denote it by r. Now I tried to compute it, and as you can see here, after 1 million terms, n equals 1 million, I get that number there. But Broukamp found that number. Quite a bit different from this number here. I should say, by the way, I met Broukamp probably 40 years ago. He worked for Eindhoven University in Holland. I just remember him vaguely. He was an old man then, and I was relatively young. Anyway, why is this so? Well, it's because the series converges incredibly slowly. So there's a need to speed it up. And one way is to use the Weierstrass factorization theorem, which, for entire functions, it's just, I'm sure you know all this. If you have a polynomial, you can always write it as a product of its roots. Well, you can do that for entire functions if you know what the roots are. And of course, we do for sine function. And it's convenient to choose the sine function. We choose also x equals pi squared upon 2, and then we expand this. Well, expand is wrong, perhaps. I just take out 2 terms here. This is... Oh, desculpe. Obrigado. What we do here, then, is to just take out the first 2 terms. Here they are. And then we flip this over, inverse, and the sign comes down here. We can compute this number, and then what we do is we define this here, and we compute the partial products of Q. And of course, we then Rn is just then P times Qn, because the P's will cancel and you're left with what you want. And indeed, this converges fairly quickly, not that quickly, and you get the number that, Pickover and Broukamp got. I may say that you can speed up this convergence by using more of these terms here, but I haven't actually tried that. This is an interesting theorem, Morley's trisector theorem. You take any triangle and you trisect it, and what do you get when you join the trisections? You get an equilateral triangle, which I think is surprising. Now, you can prove this, as I did, by, it's no loss of generality, by taking this on 0, 1, and then defining the triangle by the theta angles here and the phi angles here. So you've got 3 cos theta, and it's convenient to do it this way. This allows you to calculate simple coordinate geometry, all these points, and then you can show that this is an equilateral triangle for all theta and phi. But Morley, not Morley, yes, John Conway, sorry. He had a much neater proof. He actually started with an equilateral triangle. It's a constructive proof. And then he patched together the various bits to produce an arbitrary triangle. I won't go into that argument, but I've got the paper with me if anyone wants to follow that up. But one thing that I noticed, which I think is quite interesting, is that if you pentasect, you take 5 different sections, what you get is not just an equilateral triangle, but you get another equilateral triangle within it. And furthermore, if you keep intersecting, you appear to get an infinite number of equilateral triangles. Now, here's another result that I don't think's known. I haven't bothered to prove it because I thought I would leave it as an exercise. Now, there's another theorem that's not so well known either. It's called Viviani's theorem and generalization. What you do is you take an equilateral triangle this time. You take an arbitrary point in it, anywhere, and you drop perpendiculars, and then you can show that the sum of the perpendiculars, D1, D2, and D3, is equal to root 3 upon 2 times the length of that side. But I've taken the length just to be unity, so that you can see here, this is just, well, the way you do it is you join PC and PB. That gives you a triangle, and of course its area is simply height times the length, or half the height times the length. And if you do it with, join this as well, you get 3 triangles which make up the area of this triangle. So, and that of course is root 3 upon 2 if this is 1. So that gives you the result there. Well, how do you generalize this? Well, it's obvious with a square. You have, D2 plus D4 is 1, and D1 plus D3 is 1. So clearly, in this case, the sum of the DIs will be 2. And then you can do it for the pentagon here. So an arbitrary point here, you drop perpendiculars and so on. And you can do it generally for a regular, this is a regular n-sided polygon. Where we take an arbitrary point, drop perpendiculars, and I'm not going to say, it's very easy to work this out. We get this here. And in the case of the square, of course, it's that, and that should be a 5, apologies. That's the case of the pentagon, and you get this result here. But note that I've defined E1 and 1 minus E1. So for a regular polygon, you also get another result, which is this. It's the one on the top here, that summation EI is equal to the summation of 1 minus EI, and that is equal to n over 2. Again, I won't prove it. It's not difficult. But much more interestingly, in my view, is that if I take an irregular polygon, all right, so see this as an irregular polygon, then what I can do is I can write A1, that distance, squared, plus A2, B2, that distance squared, plus A3, B3 squared, is equal to B1, A2 squared, plus B2, A3 squared, and so on, which gives us this result here. Now, this is simply a generalization of Carnot's theorem. Remember, when we came in, Carnot's theorem was an arbitrary triangle, and you had that, well, A1 squared plus B1 squared plus B2 squared equals the other bit. Well, this is exactly the same, but for irregular polygons. So it's a complete generalization. Again, it's not overly difficult to prove, and I won't do it. But again, I've got the article with me if you're interested. So this more or less comes to an end. Finally, this has really been a rapid tour around some little-known Euclidean geometry. I hope it has reminded Potty of his school days when he was a young boy. Congratulations on getting to the biblical age of 80. Feliz aniversario. Thank you.
Thank you, Sean, for this wonderful talk. Very, very nice, very fascinating, these things. Let me just start asking a question. What did you make you interested in this type of study?
That's a good question. Perhaps old age and retirement. I think when you get to a certain age and you don't have the pressures to bring in money for your university, you feel that you can actually go back and study the mathematics that you loved when you were a child. Well, almost a child. Certainly it would be around 14, I suppose, 12, 13, 14, when I first was introduced to geometry. And it was just maybe returning to childhood. Perhaps this is normal for someone who's 80 years of age.
Very good, very good. Congratulations for that. Someone has some questions? Anybody? Yeah, Alberto?
Thank you for your talk. Just a comment. I think that Carnot guy is the same of the Carnot cycle in thermodynamics, which is the theoretical cycle which any cycle can have.
No, you're absolutely right. Yeah.
I think it's.
He was a bit of a polymath, you know.
Yeah,
he
yeah.
wasn't just a mathematician. I think he
Yeah,
just
exactly.
dabbled. Yeah. No, yeah. Good.
More questions? No? Michael?
This is maybe the difficult question now, isn't it?
Now it comes.
This may be a trick question. Shouldn't it be 4 score minus 10?
Shouldn't it?
4 score minus 10.
Oh, have I got that wrong? No, it's 3 score, isn't it? 320s are 60 plus 10. No?
Yeah, but you had 4 score, so
Did I have 4?
okay,
Oh, desculpe.
okay.
I never could count.
We have another 20 years to think about it anyway.
Muito obrigado.
Yeah, very good. Any more questions? Anyone? Yeah. All right. If no more questions, let's thank Sean again. Now we have a coffee break, and then people that will go into present posters can hang the posters, I guess. I didn't see what's happening over there, but perhaps it's ready for you. And then we resume 40 minutes later. Let me see here. We resume at 10:30 for the presentation of Álvaro Coutinho. Thank you. Yes. everyone. Welcome. Let's start our second part after the coffee break. It's a pleasure to introduce you Professor Álvaro Coutinho, that's the next speaker. He is from Federal University of Rio de Janeiro and also a council member of the ABMEC, it's a Brazilian Association of Computational Mechanics. He's a member of editorial board of many important journals, and he's a very well-known researcher. His interests are in high-performance computing, and right now he's doing a very good research about bridging the gap of AI or AI tools and computational mechanics. And yeah, something that I wish to do also. So I'm very interested in that. So, okay, so he's going to talk about recent advances of data-driven methods for coupled flow and fluid transport. So welcome, Professor Álvaro Coutinho. Thank you, Álvaro, for coming. Thank you.
Can you hear me? Well, okay. Again, it's a pleasure to be here, Putin. You're the guy. Thanks a lot. I do remember, you know, I mean, maybe 20, 25 years ago, coming here to teach a course on finite elements for PDEs. Do you remember that, Putin? Fabrizio, Norberto, yeah? Okay, I mean, and I'm glad to be back. I realized that I haven't been here since the pandemic. It's quite a while. Okay, as Fabrizio said, well, I mean, recent advances in data-driven. Everything I will talk to you today is related to the oil and gas applications in oil and gas, because in Rio de Janeiro, we used to say that we are kind of Houston in South America. Everything is oil and gas related. You can see the picture up on the left is the called Santos Bay. Oh, yeah. You have to give him, grant me 5 more minutes, because I've started laughing all the time here. Anyway, on the top right here is the situation of the Santos Basin, the biggest oil production area in Brazil. And you see here, you see my mouse now. Anyway, everything we see today is about us on this is seismic imaging, is you know, I mean, wave propagation, inverse problems to see what is under the subsurface. But the geologists have to interpret this and solving problems like evolution, and try to understand how this reservoir are formed. We see turbidites or salt turbidites here in salt formations. This is involved, you know, I mean, understanding this process in terms of modeling and mathematics, involving multi-scale, you know, multi-physics problems. And then when you see the reservoir, you do a lot of modeling on multi-phase flow in porous media in order to optimize production and understanding, you know, I mean, explore the area. So, I mean, this is oil and gas perspective. The agenda for today is, as Fabrizio said, how computational science, engineering, high-fidelity simulation, and scientific machine learning blend, in a sense. And I'm going to show you 3 applications: turbidite currents, highly Bénard flow, which is a paradigmatic thing like the salt formation. Salt formation is a thermo-viscous flow, coupled thermo-viscous flow problem with a highly nonlinear equation of states, but highly Bénard is a model problem for this, let's say. And then multi-phase flow in porous media. And I will concentrate on the topics that you see on all these applications. And then some final remarks on application. Okay. There is this computational science engineering life cycle. You see, you start by the problem description, and then you put some equations, for instance, coupled fluid flow and incompressible flow, transport, and so on. Then you do algorithmic model, you know, I mean, finite elements, for instance, finite volumes. Then you run this in a supercomputer, And then you produce nice picture. If everything else fails, show pretty picture. So I mean, this is a kind of a turbidite current, which is a I mean, turbulence, sediment deposition, sediment transport. They are all problems at stake here. So we have been doing a lot of high fidelity simulation of those problems. For instance, you see, you know, I mean, a turbidite currents, columns, volume of fluid computations with no Newtonian flow, two-phase flows, and things like this. In the right corner on bottom, you see the interaction of a drop in water coming into water and multi-phase flow in porous media. Yeah, I mean, I said computational fluid flow and transport. So I've been problems we have. I mean, for the source term and then handle in several ways. But then we play the arena on scientific machine learning. Again, those high fidelity simulations can maybe too computationally expensive for some application of problems. Scientific machine learning crafts a new generation of machine learning applications across science and engineering. And then, you know, machine learning is good for understanding patterns, future time predictions, proxy model for numerical simulations, and systems identifications. So we need surrogate modeling. You do, for instance, where scientific machine learning is important, what we call the outer loop. For instance, optimization, a certain quantification, design, and so on. So we define a physical and mathematical model. We do a parametric space to be queried, all this stuff. We compute this n q times, I mean, as many queries as you want, and then compute. So this is usually the simulation workflow is the kind in blue. On top of this, we have this, you know, the kind of outer loop that happens in optimization, a certain quantification, parameter exploration, so on. So we usually do a pre-processing, measuration, selecting parameter, do a time stepping, adapt mesh, solve nonlinear equations, so on. And we have to do repeat to cover, you know, the many queries task at hand. I don't have the time to go to this, but the better we can do is optimal complexity of this loop is order of n. N is the number of unknowns, number of degrees of freedom to the power 4(3), and I'm 4/3. And I'm assuming here that your linear equations are being solved with optimal complexity, which is achievable in theory by multi-grid methods, which means that this bound here is quite optimistic. And that tells you that the only way to reduce complexity is by adapting time and the mesh as well, okay? All right, but then, I mean, compute to generate data. So we can think about a scientific machine learning surrogate model where you don't compute this number of queries. You train for a number, train the surrogate model using a number much less than the number of times you're gonna do the queries. And then select the metrics, verify generalization, verify if it's compatible with the physics, and then you have a trained scientific machine learner to explore, and everything is a good idea that if you predict the remaining queries using the surrogate and thinking that the inference wall time is much smaller than simulation wall time, then okay, scientific machine learning is a good idea, and then you could do surrogating for all this kind of problems. As I said before, we're gonna do these applications. We're gonna see, you know, flavors of applying this idea of scientific machine learning around turbidity, current, thermal flows, and multi-flow in porous media. Yeah, nice pictures, and let's move on. Well, turbidity currents, we're going to examine how far can we go with a linear model, dynamic model of composition, with the challenges are modern analysis of complex fluid flows, improving DMD efficiency for large-scale simulations, and assess DMD time prediction capabilities. I will not go into all this. And in a nonlinear model, we have defined as parametric surrogates based on neural network with a two-stage dimensionality reductions. And of course, as a demonstration of a surrogate model for parametric exploration. Okay, linear model, dynamic model composition is interesting. There's a huge literature on this. And it needs observation for the nonlinear problem at hand, and this observation come from snapshot of a large parallel simulations. DMD minimizes, produces this approximation for a linear operator relating a matrix collecting snapshots with a one time step of difference. It's related times n plus 1 to time n. And we arrange all this. We produce an approximation for the inverse of this operator and truncate. The nice picture on your left show the modes. The top is you can see is the simulation, a simulation snapshot where you can see the Kelvin-Helmholtz billows, and the other things are modes, are the dynamic modes of the composition. So we do it, computing the pseudo-inverse is expensive, and the matrix conditioning. What instead we do is a computer approximation to the eigenvalues doing a singular value of the composition. On the picture on the right here, you see that comparison between the eigenvalues of the true operator and the approximated one. They're quite close for this particular problem. And the question is, if we are throwing away data for computing the pseudo-inverse, why do we store it in the first place? So this is, you see, we're going to see then linear model, DMD, how it goes. As I said before, in high fidelity simulation, the only way to diminish, the computational complexity is by doing time steps, adaptivity in time and space. So you use the snapshots of data. What we do if your snapshot doesn't belong to the same space? If you do refine mesh, adaptive mesh refinement space, you produce patterns like this. And things like on your right, that it has the same number of degrees of freedom, but the mesh is not topologically equivalent there. So, those snapshots, those data, they don't live in the same space. How to compute a singular value in the composition for those data? So, what we do circumventing this problem is doing an L2 projection of the numerical simulation results on different meshes on a kind of what we call a reference target mesh. How it works? For instance, in the simple problem, you see different projections, and the L2 projections follow a linear system. We prove this theorem in the paper in yellow below. And it say that if every degree of freedom in the original mesh is also a degree of freedom in the reference mesh, the projection is a full rank matrix. Oh, good. So we can guarantee this. In practice, having a reference mesh representing the defined scale is enough for practical purpose. Before you ask, you see, we are not using the projection to compute, so error do not accumulate. It's just a representation of a snapshot, taking part of thinking that we are approximating the eigenvalues of the dynamic mode decomposition. So we have at least a reference mesh where we can compute a singular value of the composition for everything. So how it goes? On top, you see the adaptive simulation and the mesh. In back, we see the projection or reference mesh, and then a fixed mesh with equivalent resolution of the projected mesh. Everything is okay, and you see in below in the graph below the mass conservation with the solution. We see the fixed mesh, the adaptive mesh with the same resolution, and increasing. solutions with 50 degrees, 50 snapshot on the basis, 100 and so on, and they all seem to converge very well on mass conservation. More important than this, as you improve the rank of the MD, you see the relative error is, by 150 terms on a singular value, the composition is, fairly well. This mesh has, it was, I forgot to tell you, is 700 by 200 cells, which we multiply by 4 is a lot of degrees of freedom, and then we have just 200, 150 is a surrogate model that represents us very well with a speed up of 2 orders of magnitude speed up. So, okay, good. Now let's move gear of a parametric problem. We do a fully coupled RBVMS solution in Phoenix. This is the mesh. Crash off is something about power 10 to the power 6, which means it's turbulence. I mean, turbulence in 2D, okay, but okay, it's turbulence in 2D is debatable, but people say it's a nasty regime. Let's put it this way, okay? So, and then there's some experimental evidence and quite clear that the slope of the channel somehow governs the flow of this the sediment flow. And then we have a train set of slopes belonging to 0 to 10, and you can see the full order simulation, the high fidelity simulations for 4 of those things. This will be our training set. So we set up this first a sequence, a data-driven nonlinear manifold round. When we do a first linear reduction, and then we train an autoencoder to get a nonlinear manifold, and then we do a reconstruction and train another neural network to produce the predictions. You see, this is not, there's a paper from the group behind, and it has been inspired on some other works that you can see in the yellow box. So does it work? This is, the big table, you see the hyperparameters, and then we compress everything on the autoencoder for one thing to size 16, and with the linear reduction and without the autoencoder, we need 270 things, and it is the size of reduced model. Without encoder, we compress everything in a nonlinear manifold of size 16. So you can see on the top, this is a movie, yes. You can see on the top the full order reconstruction, full order solution and the 2 reconstructions, and the data generation for 30 hours, offline training is 1.5 hours, and online prediction speed up, 1 angle, all times 500x, and 1 angle, 1 times 10,000x speed up, which a good error. As you can see, we use this time scale or dynamic time warp or distance, which is a proper metric for measuring error on this. This is equivalent to is a different L2 norm for time series, basically like this is a distance. You can see that the solution on top is 5 degrees, which is not on test angles, 5 and 7.5 degrees, and below is an extrapolation. There's an angle that was unseen and outside the training set, and the prediction are fairly good. A more detailed look on the timings, as you can see, as I said before. Oops, get back. As I said before, something 10 to the power 6 is speed up, with accuracy. So, if you think of doing optimization, parameter exploration, is really pays off. On O'Reilly-Banner, this is coupling of compressor Navier-Stokes equations with salinity and temperature gradient is a model problem for salt formations, and it's to understand how the deposits and become clear in Santos Basin. We have been playing with this problem for many years, and what we're gonna see here is the nonlinear model will be a neural network, and we're going to understand when the linear basis, the POD basis, a linear basis SVD is not enough to cover, to generate a manifold, and then we have to rely solely on nonlinear manifolds to reduce your data. So this is quite, this is our paper and so on. Linear model, POD. This is interesting. We have this data set on problematic, data sets. This one comes from Spectral. They have all this branded, all this Rayleigh number. You're going to see Rayleigh to the 10 to the power 6 and Rayleigh to the 10 to the power 10, which is really turbulent. And the idea is, can we use a data-driven method to compress or to understand or reproduce this behavior to the 10 and Rayleigh 10 to the power 6? Yes, but not with a linear reduction. Okay, why? For this problem, low-rank structures do not dominate the flow. A POD base relying on a singular value in the composition, we're going to practically comprise the whole singular vector existing in your data. We have here 200 snapshots, and we need, to cover, for the case of 10 to the power 10, around 190 modes. So it makes no sense. This is called the Kolmogorov N barrier. You don't have any, your data cannot be represented by a linear manifold. So what's the idea? Well, a nonlinear model, which is be a beta variation autoencoder, which is a probabilistic autoencoder and the decoder, and it provides you a disentangled representation latent space. We have to pay attention on the reconstructions versus the disentanglement of your modes. The loss is then composed by a loss on your data, but the Kullberg-Leibler divergence, which somehow gives you a hint of the probability distribution of your data. And then you enforce those things and then produce a representation in your latent space. Okay, so for different betas, which means regulates, beta regulates basically, if you look at the loss, regulates how much disentangle and orthogonality we are imposing in your data and compare it to the representation to fit your data, right? So, for several then, we can see net F is the, and the error in the Frobenius norm, and G is orthogonality. And running on a NVIDIA 800, we can see for Rayleigh to 10 to the power 1 to the power 10 to the power 10, we can really reconstruct it very well for those two betas here. So it's the nonlinear manifolds can represent very well your data. This is how the evolution of a beta goes and the loss. You can see different colors for two betas, the total loss, the reconstruction loss for the data, and the KL divergence term, the probabilistic nature and the disentanglement and orthogonality of your data. But adaptation is everywhere. We are computational scientists. We do simulation with adaptive mesh refinement and adaptation time steps. So we learn how to adapt. We know how to adapt time steps. We know how to adapt to the mesh. And we also know who adapt the weights of loss functions. For instance, in physics informing neural networks. We know this. We know how to do this. When you think about the loss term, you can really understand that balancing the beta variation autoencoder loss can be recasted as a multi-objective optimization problems. And then we have done that with physics informing neural networks, and we can do exactly the same thing by balancing this loss automatically. The computer science literature is full of examples of people doing this. One of the famous ones is the annealing on the left. And what we are doing is, we take some ideas, borrow some idea of those guys. We did this for pins after us. But anyway, they have a more consolidated, and we are using their software, which is Relo, Bralo, and the soft adapt schemes. And yeah, it's kind of works very well. And then if you see the table, we reconstruct the norm, the Frobenius norm, and orthogonality fairly well. And it's important to see how the solution, the Pareto solution of this multi-objectives problem is completely different than the standard annealing or the process of balancing the KL divergence term people use in computer science. This is a thing that we can merge towards. Anyway, to finalize, let's move to reservoir simulation. Is a fundamental in understanding reservoir performance and fluid dynamics. Several benchmarks are proposed. We are seeing one, the SP10 benchmark, and model 1 in 2D, model 3 in 3D. We are seeing the water saturation on the reservoir. And this is a multi-phase, multi-component flow with Darcy laws and several transport equation, couples transport equations. And our aim here is to build a surrogate based on neural operators. Neural operators is an emerging technology that learn, this is our paper. It's out there in the jungle right now in JCP. What we see is, you see, standard machine learning is what is in gray. Maps the function is one-to-one and supported by what we call the universal approximation theorem. Now, it's much more important for us in the PDE business and simulation business not to learn one particular PDE or surrogate with a particular boundary condition, particular initial condition. We have to learn family of functions. We have to learn operators. And the theory behind this is the universal approximation theorem for operators, that maps the operator, and then we learn the relations of one to many, and which is much more appropriate for developing surrogates. Two technologies emerge. The Fourier neural operator with kernel is a spectral convolution. The lower frequencies are retained, and time can be treated as a fixed dimension or in a Markovian autoregressive setting. What I'm gonna tell you is it's Fourier expansion. So if you have 3 dimensions in space and 1 dimension time, all your tensor will be 4D. Doesn't scale very well for practical problems in reservoir engineering, okay? Where we see millions, hundreds of millions of cells. Our solutions, the other very interesting thing is what we call the neural operator, where we have 2 networks, a branch and trunk, and the branch maps the discretized input, and trunk is responsible for mapping the query points. The query points, if you think about the time, is the couples, space and times, and then it makes a thing much more appropriate for scale. Our solution is somehow merge the 2, as you're gonna see. Okay, we're gonna put in the branch as a Fourier neural operator, and the trunk MLP or a Kolmogorov over Aron network. So we have this pipeline here, which comprises this data generation, pre-processing. We use NVIDIA physics in a neural operator for Fourier neural operators, and the metrics. And we use poetry, weights and bias, Hydra, etc., to orchestrate everything. So we train 2 things. We train a lot of models. One first thing, note FNO is Fourier neural operator. MLP is standard MLP, CAN is Kolmogorov networks. We train 3 models. One model, A, is 127K parameters. B is 1 million parameters. C, 20 million parameters. And you're gonna notice the absence of a pure Fourier neural operator. Why? It doesn't fit in memory. We cannot fit in a 8100 for this SP2 model 2, who has 1 million cells data on a 4D tensor. So we have to go hybrids. So we train in all this model. We observe that for the model C with 20 million parameter with FNO in place, we have a very good, very good error indicator, but for the pure deep neural net, either with MLP or CAN, Model C cannot be doing this. Training time is about 1 day, or on let's say a device which is a state-of-the-art device, and then this is the training time, and then this is what we get. We are going to see a snapshot of oil saturation at 1,000 days. The Z direction magnifies 5 times, and see the ground truth. And the hybrid screen predictions for the KC is a very good prediction. On the right, you see a plot of the errors. You see that in general, all over the domain, now we have very good prediction, and in some cells, you see red spots. That mean the error is big there, but it's considered fairly good. But more strikingly, it's all the models, case E, A, B, C. Remember, case E, 100,000 per meter, case B, 1 million per meter, case C, 20 million parameters. They are able to recover, one of very important condition on reservoir engineering, the sum of saturation is equal to 1. There's no physical performance, anything on the loss, but the physics is there, thanks to the mix of a deep neural operator that learning, learning family of functions, and combined with the expressiveness of a Fourier neural operator in space, and we are able to recover the physics. I think I'm reaching the end of my talk. The final discussion here. Computational science engineering, as we know, and scientific machine learning are extremely correlated, more than we could imagine, let's say, especially in the case of coupled fluid flow problem. High dimensionality, we handle high dimensionality by doing reduced order model. And then especially important on parameter exploration and certain quantification, etc., you need surrogate modeling. If you do want time prediction, parameter exploration, neural operator is open up avenue of exploring this with highly interesting ways of doing this. Underneath all thing here, HPC is a fundamental enabler for both CSE and scientific machine learning. We are seeing the convergence of the architecture. Everything now is GPU based and so on. And now, we learn how to explore and have to be very sophisticated in our high fidelity simulations. Now, we need to learn and understand very well what is the jungle in the machine learning communities, what the jungle is, the community of machine learning is producing, and how to best explore post-board. I can tell you, if you want, in the questions, I can tell you one single thing that worries me a lot between the interplay of simulations, HPC simulations, and machine learning. Of course, data compression is always a good idea. We do, when we talk with people from machine learning, we have to realize that we do somehow data compression all the time. We practitioners in high performance computing simulations, we live in the world of 64-bit arithmetic. Machine learners live in the world of 32-bit arithmetic. So we do compression all the time, but we can compress even more. By carefully choosing this nonlinear manifold, we have C compression for a latent space of size 16 of a problem which involves turbulence, which is amazing. Of course, efficiency in CSA and scientific machine learning is crucial for scaling. When I say efficiency, is not only buy more GPUs and buy more power for GPUs. We have seen, for instance, a example of a clever algorithmic constructions, a hybrid method with deep neural net and Fourier neural operator that enable large surrogates in porous media flow that, it was considered impossible to fit this surrogate in one GPU. Yeah, it's possible if you are clever on your algorithm constructions. So what we learned in the past, that advancement in computational science engineering is on one hand, we're going to have faster and faster computer. In the other hand, we have to be smart in constructions, new algorithms to fit this new machine. The same thing will happen in scientific machine learning. Exactly the same. One thing that we're going to see more and more is this agentic AI, which will orchestrate the CSE workflow and the scientific machine workflow and the coupling between both of them and helping to discover new science. We are doing this. We have agents behind all this and in applications. If you're interested, come to me. I have some movies here that show the agents working and so on. Okay. Thanks for time. I believe I'm on time. Thanks for attention. I'll be happy to entertain some questions. Thank you.
Thank you, Álvaro, for this wonderful talk.
I was forgotten. I was forgotten this.
Yeah, that's the most important slide of our presentation.
Yeah. Who the hell pays for all of this? Those guys. Thanks.
We have time for a couple of questions. Oh, I have one.
Only one?
Yeah. What is the thing that bothers you most of this? The thing that you say that you're going to tell you that bothers you about the interplay between scientific machine learning and...
It's, okay. This is one of them. There are several things bothering me, but this is one is really... Okay, we have a clever way to put your snapshot in the same space. Okay, good. And then we do a singular value decomposition. But for really big things in 3D, like one of those here, how we compute the solutions? We do domain decomposition. We partition the mesh, okay? We partition the mesh. So the mesh, for a really big simulation, you never concatenate your output and the data lives scattered in your file system, right? Okay. But to do a singular value decomposition, the best algorithms, come on, man. Okay, to do a singular value decomposition, the best algorithms requires your data to be concatenated, and the parallel solution for singular value decompositions, the decompositions doesn't match your domain decomposition for your simulations. So you have to somehow, if you do a really huge simulation, a supercomputer, you have to pick up your data, concatenate everything, and repartition again to call the singular value decomposition to build your reduced order model. If you do beta variation autoencoders, your tensors doesn't respect your mesh partition. So there's a gap between the simulation, high fidelity HPC simulation, and the software stack for doing machine learning. And then I think we have to somehow try to bridge these gaps in order to really merge the things being the data-driven. I mean, streamline from your HPC machine to your stack, software stack for machine learning, streamlining without even changing your data. This is bothering me. You see? You understand what I'm saying, right?
Yeah,
Okay.
I do.
João, you too.
Pretty much. Thank you. Other question? You, Pucci?
Oh, sorry. Álvaro, as we know you've been a long-time advocate of the deterministic approach to these simulations. have you been bitten by the blue fly?
Look, we have been doing a lot of UQ. I mean, what I'm saying is, here, oops, yeah. I think our view here is we encapsulate all the simulation within this red loop here. That it's much more complex. It's like can involve Monte Carlo, Koopman's functions, anything you want, Langevin inverse problems, and then everything is encapsulated on this. And we have been doing this a lot. And I firmly believe that when you go to the probabilistic space, you have to have a very well-designed surrogates in order to make possible to explore the probabilistic space. Otherwise, it's practically impossible.
Are you satisfied with the results?
Well, I mean, there.
Maybe I didn't explain what I meant by bitten by blue fly. The results are satisfactory from the point of view of precision and time, and because in your case, training the training data is quite difficult to get, isn't it?
Sure. This is I mean, I understand your point right now. I mean, there's a balance. I mean, and everything works if, oops, yeah, everything works if there are complex. I mean, there's two things in place here. We have to realize, oops, yeah, we have to realize a way of amortizing this cost, optimal complexity, over multiply by NQ, the number of queries, okay? If for a particular problem, the number of queries, the training set is much smaller than the number of queries you do, yes, and if you have data and train everything, the predicted remaining one, and then everything works well. But look, those are theoretical complex estimates, and you have to be verified in practice for every case. But the only thing I can tell you firmly that this order of N43, this number is really correct. And with very tight assumptions, for instance, you are solving your linear system equation with optimal complexity, which is not true in most problems in practice, okay?
Okay, let's thank Álvaro again. Thank you.
Oh.
Sorry, Sean, for the sake of time. Well, I'll let Roberto introduce the next speaker.
Oops. Let me get out. Just one second.
Hello, everybody. Well, it is a great pleasure to me to introduce Bruno Rocha. He is an Argentinian guy, some of that expression way. And well, I will briefly comment on his background. He is currently a researcher at the Geophysical Institute at the University of Bergen in Norway. And he holds a PhD from University of Cordoba in Argentina from 2013 in the area of structures, multi-body dynamics. He worked with Alberto Cardona, perhaps some of you know him. He works in he's interested in several topics like data-driven computational mechanics, which is his presentation about today. aeroelasticity, offshore wind energy, mechanical and aeronautical engineering. I don't want to take too much time, so I will let Bruno to present his work. Thank you.
Thank you very much, Roberto, for the nice presentation. As Roberto told you, I will present this topic that is called data-driven computational mechanics, and in particular, the question that we are asking ourselves is that if this kind of approach can reproduce nonlinear phenomena, like, for example, basins of attraction, chaos, synchronization, etc. But before starting with the technical talk, I would like also to thank the organization committee for inviting me to this workshop. And also, even though I didn't have the chance to collaborate with Professor Cuminato, I did some research in the web, and indeed I found out that he is a very, very important guy and contributes a lot to the computational mechanical community, applied mathematics, and scientific computing as well. But also, as an Argentinian, I knew Professor Gustavo Buscaglia, and also, as far as I know, was Professor Cuminato who brought him here as a professor. So in that regard, I would like to say, or I would like to mention that Professor Cuminato is not only an outstanding or a very well-recognized scientist, but he has also a very sharp eyes to recognize young promises. So thank you very much. So now I will move more to the technical part of my talk. And this is more or less the roadmap for this 30-minute talk. I will tell you why this question matters, why this question about can data-driven approaches or computational mechanics reproduce chaos or these very highly nonlinear phenomena. Then I will talk a little bit about nonlinear dynamics, the data-driven computational mechanics core idea, some benchmark. Here you are going to see that I choose very simple systems like the Duffin equation, Van der Poel-Duffin equation, and Kuramoto oscillator. They are very simple in a way, 1 degree or a few degrees of freedom, but actually they are very rich in nonlinear phenomena. And then I will tell you what is working well with this approach in the context of nonlinear dynamics, and what is not working so well, and what is our next step. So, and then I will tell you a little bit about our current collaborations regarding this topic with several groups around the world. Okay, why these topics matters? Okay, actually, I am working at the University of Bergen in the Offshore Wind Center, and mostly we are doing offshore wind energy. So we are dealing with very large blades and wind turbines, and also I did my PhD in micro air vehicles in the past in computational elasticity. So we are still doing some stuff regarding aeronautics. And all these systems are very flexible, and they are switching regimes when the operation conditions are changing. And normally we have very nonlinear phenomena going around with this kind of a very highly flexible structures that are interacting with the surrounding flow. So that is why it's one reason why we are interested in if this kind of approach can reproduce nonlinear phenomena. Also, prediction is, in this case, in nonlinear phenomena, prediction is not only, to get the signal, to track the, the trajectory or the velocity as a function of time. Also, it's about the structure. We are interested in see if we can capture, for example, a flatter velocity, basins of attraction. That is about the structure of the nonlinear behind the physics we are trying to understand and to solve with this kind of a data-driven approach. Nowadays, also, we have a lot of data that is available coming from measurements and from the field. And also, of course, we can generate synthetic data from simulation, for example. So the challenge here is how to integrate this data into simulation. So the central question, I would say, can data-driven computational mechanics, this framework reproduce not only the trajectories, but also the structure behind, like for example, as I said before, resonance, branches, bifurcation, cascades, limit cycle oscillation, quasi-periodic orbits, chaos, synchronization, etc. So in that regard, that is why also we choose these very simple systems like Duffin, Van der Poel, and Kuramoto. So let's try to decode a little bit the question I posed before. So we have, for example, we can identify in the title or in the question, like different fields of science, like nonlinear dynamics. Also, we can identify their data-driven. Also, we can identify machine learning. Actually, our data-driven approach or data-driven computational mechanics is a sort of unsupervised machine learning. Of course, those people working with machine learning, we have supervised machine learning, unsupervised machine learning, and different approaches. Our idea or our DDCM is a sort of unsupervised machine learning where we are going to replace the constitutive manifolds directly by data. And we are going to keep, or we are going to satisfy equilibrium or balance equations and compatibility equations, etc. Okay? And then, of course, we have the phenomena we want to study. Like, for example, in this case, I put some of them, chaos, synchronization, and basins. But we have much more nonlinear phenomena depending on the system we are studying. So I think I can use this, huh? Or not? Okay, maybe not. Okay, thank you. But can I switch with this? No. Doesn't matter, don't worry. No, don't worry. I will do it. No. Thank you. So, what about nonlinear dynamics? Okay, in nonlinear dynamics, depending on the system we are studying, for example, we know that very small changes in the system can, go to a very different behavior. For example, we know that chaos, for example, if we perturb a little bit the initial conditions, we can end up in a very different state in chaotic regimes, for example. So again, the important thing here is not try to reproduce only the trajectory or the velocities or accelerations, etc., like as a function of time. We want also to try to capture the structure behind, the object. What is the basin of attraction? What are the boundaries of the basin of attraction? What are the limit cycle oscillation? Can we capture, for example, a flatter onset or critical velocities behind Hopf bifurcations, for example? So that is more or less related to the question we want to answer. So let me go to this one to show, for example, some examples. Here, I will talk about this kind of chaotic behavior like you are seeing on top to the left. And here you have an example, for example, when is occurring, for example, chaotic behavior. You have this kind of wheel that is, pouring water on these kind of baskets. And then some perturbations, small perturbations can, drive you to a very different state. This is one of the examples. There are many examples of chaotic systems. Also, maybe you may know the Lorentz attractor, and it's coming from forecasting. So there are many examples. Then, for example, this other one, this is related to the Van der Poel-Duffin equation, this bifurcation curve that is on the bottom to the left. I will talk a little bit about this one. But the example I will show you is a flatter one, because I am coming from aeroelasticity community. So in aeroelasticity, there is one phenomenon that is a dynamic phenomenon that is very destructive. If a plane, for example, entering flutter, probably is a very bad thing for the plane. So, and actually, this kind of a flutter is characterized, the system is characterized by a supercritical or subcritical Hopf bifurcation. So it's important if we are going to, bring this DDCM to study aeroelastic behavior of very highly flexible structure, it's very important that we can predict with a very safety factor the onset flutter velocity, because it's a quite destructive phenomenon. So also, let's go, for example, to synchronization. This is another nice example where synchronization is happening with these metronomes. For example, you have several oscillators, right? That is vibrating at different frequency, different period for maybe, for example. But what happens if we mount this kind of a set of oscillator on a common base? You're going to see that after a time, all these oscillators are oscillating to the same frequency and the same with the same period. You can see that is more or less they are all almost synchronized. So also this is a very nice phenomenon to understand. And also if we are bringing DDCM to this nonlinear phenomena, this is very important because the power grid, the power electric grid actually are based on a study the synchronization of the electric generator on the grid. I mean, to function in a very safety way, all the generator has to be, synchronized and has to be has to resist perturbations in order to continue or keep functioning. For example, there is a very nice study about Norway. I picked up this one because it's where I am living now. But this is a study by using Kuramoto oscillator to understand or to study the power electric grid of Norway. And here, this one, the picture on the top to the left, is the example I choose, like 3 degrees of freedom, Kuramoto oscillator, and the one in the right is the basin of synchronization. I will talk a little bit about this in a couple of slides. And what is happening with DDCM when we were trying to reproduce this. So, let's talk a little bit about the approaches. Here, I will not dig into many details regarding what is out there regarding machine learning approaches. There are a lot of approaches, supervised, unsupervised, super vector machine. There are a lot, reinforcement, learning, etc. So I would like to mention, for example, classical model simulation, like we start, with fundamental principles. We write down the equation of motion. We consider a constitutive law. For example, if we are in an elasticity, we know that we are going to relate somehow the stresses with the strains, probably through a phenomenological law, like the Hu law, for example, if we are assuming a linear constitutive manifold. And then if we are changing the field of science and we are going to thermodynamics or hydraulic or whatever, also we can always recognize some kind of a constitutive law that is based on a phenomenological law, actually, coming from measurements in the lab, for example. So this is one approach. And then we write down, we discretize in time or space, and we perform the numerical simulation. Then, of course, with this, nowadays, this machine learning technique, also we can use black box one if we are use supervised machine learning. And of course, we have pros and cons. Every method, every approach, even the method we are using, also we have pros and cons. Everyone, or every method, I would say, has pros and cons. And then I would like to talk a little bit more about our approach. That this is the data-driven computational mechanics. Then we start also with the basic principles. So we write down the balance, for example, the compatibility equations of our problem. And then we identify the constitutive manifold. That is, in case of elasticity, is relating, for example, stress and strain. And then we are going to remove this constitutive law, and we are going to replace directly this constitutive manifold with data, raw data. We just remove the constitutive law, and we consider there, or we introduce, or we integrate a set of finite data, okay? This is more or less the core idea of this DDCM. And then, of course, this kind of approach is parameter-free because we can replace this data for another set of data, and we don't need to do anything. Of course, we are going to pay a price. I mean, everything is, not everything is free. You always pay a price, okay? This is parameter-free, very nice. But what is the price you're paying? Okay, I will tell you later. And then, of course, in this kind of the context of nonlinear dynamics, we need to try to assess what is, the performance of the DCM. And then we introduce some kind of metrics in order to assess or evaluate the performance of the DCM in the case of nonlinear phenomena. So I think now this is more or less the idea I told you before. So we keep the mechanics. Basically, we are saying we keep the physics, we keep the balance equations, and we keep the compatibility equations. So in a way, we are satisfying the physics or the underlying physics behind our phenomena. We replace the constitutive manifold by a set of data. So for example, let's go to the Duffin equation that can represent, for example, a spring that is being softening or hardening according to the sign of the cubic term, right? So we are going to extract this constitutive relationship between force and displacements in the spring, and we are going to consider points, a set of data. So the curve of the left in the central box is going to be replaced by points, okay? And then we need to solve this kind of a problem that now is a mix between something continuous, because we have the balance equation, we have the compatibility equation, plus something discrete, that is the set of data. We ended up, if we formulate this, we ended up with an optimization problem that is continuous discrete optimization problem, okay? And it's very, very hard to solve because it's NP hard, meaning that normally we have the number of data points powered by the number of degrees of freedom of the system if we are looking for the global minima, meaning that we need to, to assess everything against everything, and it's very expensive, and this is one of the prices we are paying, okay? So, okay, let's talk a little bit about the methodology behind this method. I will try to show you a picture about how we are formulating and how we're implementing this DDCM. Of course, if you have more questions, then we can chat. I try to summarize a little bit, but let's say that we are going to assume a very simple model, like the Duffin equation, Van der Poel, or Kuramoto. Then we write down the Lagrangian of this phenomena. We are going to consider external forces by using the principle of virtual work, etc. Then we identify the configuration space, we identify the tangent space where the velocities live, etc., etc. We can have holonomic constraints. Here I put the term of holonomic constraints. Also, we can have non-holonomic constraints. I didn't consider the case here. And then we could write down the equation of motion fully. Like if we are just in a course of rational mechanics, and the professor tells us, okay, just derive the equation of motion of this system with n degrees of freedom. And we write down the Lagrangian, and we take the derivatives, and we get the equation of motion, okay? But now, we are going to, before going to DDCM, we are also going to use a way to discretize in time the system in order to build our integrator. I mean, we can use different integrator scheme to integrate the equation of motion. Here we choose, because it's a very adaptable to the problem we have, a variational scheme. So in order to derive this kind of integrator, we go back to the Lagrangian, we discretize the Lagrangian, and then we ended up in a natural way in a variational integration, and this can be, for example, a two-step variational integrator, and then we can reformulate these two steps in one step in the phase state or in the phase state or in the state, and we ended up more or less with the Newmark. I mean, it's very similar to the Newmark scheme. Actually, Newmark scheme is a sort of variational scheme, variational integration scheme. So here you can find all the process. This is very, I mean, not super technical, but I mean, it's like coming from the literature of variational integration. And then I choose here, we ended up with different schemes. We can end up with this scheme with the trapezoidal rule plus the mid rule. And it's a two-step method, meaning that we need two information from two time steps before in order to move forward. And I didn't like that one, so I just reformulate the integrator in the phase space, so meaning that we are using the configuration coordinate, I mean Q, plus the momentum. And this is a one-step integration scheme. But this is just the integration scheme you want to use. I mean, you can choose. There are many options here. So once we write down the equation of motion of our system, we discretize in time, we have everything in discrete time now, and now we are going to introduce, or we are going to reformulate this problem in a DDCM framework, meaning that now we are going to identify our constitutive manifold, and we are going to extract this constitutive manifold, and we are going to replace this by data. And doing this, we actually write down now a functional that is basically, we want to minimize a distance between the continuous variables, for example, let's say the Duffin equation, and a spring. So we have the relationship, the constitutive relationship between the forces and displacement. So we want to minimize the distance between the forces and the displacement, the continuous variables, with respect to the data that we have coming from measurements, for example. And then we ended up writing down, for example, this equation, the one that is in blue, this one, this functional here, we want to minimize this functional. So here, for example, we have the displacement or the strength. We want the continuous one, and this is the one coming from the discrete data set. And we have the same with the forces. So we want to minimize this distance, subject to, we are going to consider now a set of constraints. So we want to minimize this guy, the global minimum here. We need to test everything against everything, and we ended up with this number of data points powered by the number of degrees of freedom of the system. So that can escalate very fast and very high. Okay? So of course, we are not going to use this kind of a brute force or to try to find out the minima. We are going to use something that is called alternating direction method. That actually, what that means is like we are going to fix the data. So we fix the data. So we ended up with a continuous subproblem that has a KKT structure. We solve this continuous problem, and we update the discrete data. Once we update the discrete data, we go back to the continuous problem, we solve again, and this is kind of an iterative loop until we reach convergence. And this alternation direction method can decrease the number of operations by a lot. But of course, we can get trapped in a local minima, and we cannot do anything about it, okay? That is one of the problems that we could have. So this is more or less the idea behind. We can discuss a little bit more if you have questions regard to the approach. So this is like kind of a minimal algorithm picture. It's like as I told you before. And of course, this kind of alternation direction method that is fixing, the discrete data, and we solve the continuous one, and then we go back here, we update the discrete, and we go back here and we solve the continuous one, is a sort of a discrete projection method, meaning that it's non-smooth. So meaning that in the process, this is injecting perturbations to the solution. And this perturbation can affect the structure of the nonlinear object that we are getting in the end. And this is another problem. Because of this non-smooth projection technique, we can end up with something that is not what we are looking for, okay? It's very sensitive, actually. So the idea, to try to understand what is happening, three different problems, very simple. Duffin equation, Duffin-van der Poel, and Kuramoto. Why Duffin oscillator? Why Duffin oscillator? Because Duffin oscillator, the force Duffin oscillator has a nonlinear restoring force, meaning that we can have bifurcations and alignment cycle oscillations, and also we have the forcing term, and we vary as a control parameter, for example, the frequency of the forcing term. We can have, for example, chaotic behavior. We can have double period or intermittency, like as a route to the chaos. So by studying this equation and try to reproduce this kind of a highly nonlinear phenomena, we can assess the performance of our data-driven approach in order to see if it's able to capture what we are looking for. Then we will move to the Duffin-van der Poel. Why the Duffin-van der Poel? Okay, Duffin-van der Poel has the same nonlinear restoring force, but has a nonlinear dissipation term. And also that can reproduce, can, show some kind of chaotic behavior, and also quasi-periodic orbits. For example, besides supercritical and subcritical Hopf bifurcations curves. And then we have Kuramoto, because Kuramoto, we are interested here in the synchronization basins. So this is a very nice example to try to see if this DDCM is able to capture the synchronization basin behind Kuramoto in this case. So let's start, for example, with the benchmark number one, that is Duffin. Here, always, I think here, in this case, then it's going to change. Sorry for that, because here, blue means that is the non-DDCM solution, meaning that we discretize the system and we solve it as a normal simulation technique. So we have here, for example, B stability or resonance peak. The B stability, because if you can see here, the blue curve is going up and suddenly is, going, jumping to the lower branch. So we have there a sort of B stability of the system, meaning that two possible states coexist for the same parameters. That is happening with a true system. So the idea is to see if DDCM can also capture this kind of B stability phenomena. And in the right, we have the solution coming, for example, from DDCM. Black, here we consider when we replace the phenomenological constitutive manifold by a set of data, we can consider, for example, 20 data points, 40 data points, 50, 100, 1,000 points. And of course, the method is very sensitive to the number of points that we have in the constitutive sampling. For example, if we use 50, I think, 51, we have nonsense. It's like it's jumping, close to this very, very fragile zone. The DCM approach is failing completely. It's just jumping to a non-system, nonsense curve. If we increase the number of points, still it's not working well with 101. But when we move to 151, now it seems to work very well. We can reproduce this kind of jump. And if we keep adding points to the constitutive manifold, of course, we can reproduce very well this particular curve here. So the question is, can we reproduce something else? Okay, this is a very nice example. Here, black means no DDCM, and blue means DDCM, okay? So, of course, in the left, the black one is the true solution. So we have, for example, in the top left, this kind of a 4-period doubling for this kind of forced Duffin equation. Meaning that this is a road to chaos. It's like the period of this oscillation starts, to doubling and doubling and doubling and doubling until you have a full spectrum in the Poincaré maps, and this is when you reach chaos, for example. But if you take a look to the DDCM, there is something very, very peculiar here. The same parameters. Here, I choose a number of set of data very high in order to get a very nice approximation to the true solution, but actually, we are not getting a very good approximation. If you take a look, the blue one is flipped over the two axes. It's the same attractor, but it's flipped. I mean, it's not the same because you can also notice some kind of thickening of the curves with respect to the true solution, I mean, through the numerical solution, okay? It's flip about the two axes. What happens here? Okay, I was, you know, when I was doing this, I was, what is happening here? Because why is happening, why I'm getting this flip in the attractor? I mean, and then I studied a little bit and realized that also for this kind of a cubic force, you have two coexistent attractors. I mean, you have the black one, but also in the true solution, you have the flip one, the flip around the two axes. And this is proof. I mean, if you flip the initial condition, you get to the other coexistent attractor. But in the DDCM, by using the same initial condition, I am going to the other one. Meaning that this kind of alternating direction method is not smooth, is injecting a lot of perturbation or perturbation enough in order, you know, to push the solution to the coexistent attractor. So this is something that's happening with the nonlinear, with the DDCM in this context. In the lower one, we have a chaotic regime, and here, this flipping phenomena is not happening, but you can see that the blue one is more thick in the sense of the lines. I mean, globally, we capture the structure of the attractor, but if we go finer in, like for example, if I can evaluate the fractal dimension of the chaotic attractor, the DDCM is failing. I mean, I capture the global shape, but I cannot capture the finer resolution of the attractor with DDCM. Then, for example, we move to van der Poel-Duffin, and here we investigate this supercritical Hopf bifurcation. And on the top, this black one is the solution, no DDCM solution, and in the bottom, we have the DDCM solution for different set of data. And we can see that actually the onset of the critical value, in this case of the damping, is well captured for most of the data set I consider here. But of course, the curves vibrate a little bit. The curves, I mean, the bifurcation curves is not vibrating, but it's oscillating if you want. And this is highly dependent on the number of points that we have in the data set. And also, close to the bifurcation point, if we are using a set of data with a few data points, the Limit cycle oscillation, that is this kind of ellipse, is some kind of segmented, is some kind of an hexagon. So we are getting this kind of a discrete, I mean, a segmented Limit cycle oscillation because of the few data we are considering the data points. But here, I can say, for example, that we are getting, we are succeed in getting, for example, the critical point of the bifurcation curve. And then I try, for example, moving, you know, the parameters of the external force, some kind of a quasi-periodic orbit. Again, black one is the true solution. The blue one is the DDCM. We can see, for example, in the bottom part, we have the Poincaré projection of the quasi-periodic attractor that is above. And the curve is quite the same. But if we, for example, take the Hausdorff distance between the curve, the black curve and the black curve, we see that this is oscillating, meaning that we are getting the point on the this kind of a closed trajectory, but the points are being, you know, shift. And because of that, we are getting, when we are measuring the distance between this closed curve between the blue one and the black one, we are getting this kind of oscillating phenomena in the distance. Maybe the conclusion here is this is not the best way to measure the correctness or the performance of the DDCM for this kind of very quasi-periodic orbit. This works better when we go for the same system to a chaotic regime. So, for example, in the lower part, we have the projection of the Poincaré projection map for this chaotic attractor, and we can see again that the shape is quite okay, meaning again, the global structure or the global projection of the Poincaré maps of the original attractor is well captured, but if we go finer to the fractal dimension of this section, we are not going to, didn't succeed. We don't get the fractal dimension that we should. And this is okay. We have a lot of perturbation coming from the alternating direction method. And then we have, lastly, the inertial Kuramoto problem. And here I consider three oscillators in the Kuramoto problem. And what you are seeing, again, in the black one, is the basin of attraction, the basin of synchronization of the Kuramoto problem, no DDCM. And in the blue one, you are seeing the basin of synchronization of the DDCM. Basin of synchronization means here that all those initial conditions that are leading to the asynchronized state. What those initial conditions that are not leading to a synchronized state are what is outside of this basin, is a white dot, let's say. And then we have the frontier or the boundary of this basin of synchronization. And that is the most critical part for this problem, meaning that DDCM fails always in the border. Always in the border. You can see, for example, in the blue one, green dots. Those green dots are misvalues. Meaning that are synchronized state that doesn't exist in the true problem, or are non-synchronized state that doesn't exist in the other one. So the DDCM always fails in the border in this example, for this example. And also that is quite intuitive because we have this kind of non-smooth alternation direction method that maybe these perturbations are just changing the membership of an initial condition from a synchronized basin to a non-synchronized state. So, what I can say regarding the performance of the DDCM, what works well? Okay, we can reproduce, for example, time series. We can reproduce global structure of the nonlinear object or nonlinear phenomena, the object we are analyzing, for example, Lyman cycle oscillations, chaotic attractor, the global structure of the chaotic attractor, we can reproduce that. But what is not working well is, for example, normally DDCM doesn't work well where the nonlinear phenomena is fragile, meaning that in the boundaries, in the separatrix between, for example, non-synchronized state and synchronized state, fractal dimension of the chaotic attractor, that we cannot reproduce because it's very sensitive to the non-smooth behavior that we are having because of this method we are using to solve the problem. So another question, for example, you can ask is, what should predictive mean in nonlinear dynamics? We need to reproduce or we need to predict absolutely everything, or it's okay to reproduce the global behavior, or we need to reproduce the finer behavior or the finer structure of the nonlinear object as well, okay? For now, and for me and for our group, it's like we are okay with the global structure. And we want to see if we can, improve the prediction in a finer, or to try to get a finer prediction of these objects. There are a couple of stuff also. A practical advantage of DDCM. Here we don't need to train. For example, if we were using a supervised machine learning, we need to train this, our neural networks, and every time we are changing the data, we need to retrain. With this approach, we don't need to retrain anything actually, but we pay a price. The computational cost actually is bigger. Let's say that you have already a neural network already trained. You use it, very cheap. Here, we need to solve an optimization continuous discrete problem every time. And if we are doing dynamics, we need to solve a problem every time a step. So we pay a price. This is a parameter free, but the computational cost is higher. So it's a trade-off. Some limitations and open questions. As I said before, this is a limitation in the DDCM. Like we need to solve an optimization, this continuous discrete problem every time a step. Then we can, for example, try to investigate other questions regarding, for example, what metrics we should use in order to assess the succeed or the performance of our DDCM framework. How far can this framework scale toward realistic engineering problems? These are very toy examples, so you can ask, and it's quite fair. I mean, did you try to solve a realistic problem? We don't. We just we are trying to solve, try to answer first basic questions and then move to more realistic problems. For example, what about thermomechanical consistency? I mean, for these cases, thermomechanical consistencies was satisfied. That means, for example, the product between the strains and the stress, or the displacement and the force, is always positive, for example, for elasticity. That always is the case? No, it's not always the case. Now we are solving a thermal dynamics on power electric transformers, and this thermomechanical consistency is being violated. So we need to try to enforce this consistency, or try to discard, or try to solve this problem. And this is more or less the network that we have with DDCM now. We are working quite a lot now with Roberto Ausas, and also with another universities, Barcelona, Hannover in Germany, University of Kristiania in Oslo. This is more or less the network that we are trying to, to address different problems in DDCM. As conclusions, okay, what is something that works well was, capturing the global structure of the nonlinear object that we were investigating. This is not always working well, in the sense like when we go finer, we fail. So this is a limitation of our approach. And the most important benchmark is the geometric fidelity. I mean, we need to be sure that if what we are studying, we are capturing the important stuff. For example, as I said before, if we are studying aeroelasticity in aircraft design, what is quite important is just to get the onset, the flutter onset very well, because this is quite a disaster, could be a disaster. So I think that's it. Thank you very much.
I think we have time for one question. Anybody? João, yes.
Hi, thank you for the talk. You mentioned that you're not really doing applications yet, but I'm trying to understand, or at least if you could elaborate a little bit more on how you use these ideas, for instance, for flutter or LCO, okay, inner elasticity, because you see, you focused on the constitutive relations, right? But in this case, I mean, the fluid is air, so it is a perfect gas, right? So there's not a complicated constitutive relation. And for the structures, typically too, I mean, if you look at a wind turbine blade, for instance, the constitutive relations are somewhat straightforward. I mean, so how this whole thing would fit if you were to do some elastic analysis of a wind turbine?
For example, I can say in the case of our wind turbines, let's say, I mean, I agree with you that from the fluid or the flow, is not much to do there. But from the structural point of view, I mean, a blade or an aircraft, a new aircraft, normally you have composite, and then you have a very complicated constitutive law. You can have anisotropic behavior, you can have orthotropic behavior. And then also, if we are going in the direction of digital twins, for example, and we fully instrument, for example, a blade, we can have real data coming from the measurements, like displacements or deformations plus stresses, and we can feed our model in real time, because, I mean, we don't need to retrain anything. It's like we are adding points, and our solver is still working. Of course, we pay the price of a little, computational cost, right? Because we need to solve this optimization problem. But let's say that the blade is being degraded because, I don't know, some storm in the North Sea. In Norway, we have a lot of problems with ice accumulating on the blades, so that the blades can degrade a lot. So if we somehow are just feeding our model with real data, we can measure, for example, the stress and the strains, and we can see this degradation in this point, in the set of points. I mean, the nonlinearity and the degradation is being encoded in the set of data points. In that case, I would say that it's quite nice to have something is coming in real time to our model. So we can, for example, be ahead of predicting some kind of nonlinear behavior that is happening. But we need to be sure that we are able to capture this nonlinear behavior.
Thank you.
Álvaro?
Thank you, cool talk. Let me ask you, I mean, for instance, in your minimization problem, first, let's say stress, strain, are you imposing symmetry, for instance, on some, I mean, on all those chaotic and dynamic systems, there are some properties that perhaps if you don't impose in the neural networks or your formulation, maybe you can miss something. Can you comment, please?
I mean, you mean, for example, asymmetries in the data set or in the because
For instance, in the dictionary and stuff like this.
Because, I mean, we are not imposing any kind of symmetry. I mean, we are formulating this minimization problem as a minimization of a distance between the strain and stress forces and continuous force and forces coming from the data set, satisfying only equilibrium and compatibility, what the laws are telling us. But we are not, you know, imposing any additional stuff, any symmetries on the data sets or anything like that. Also, we test like adding noise to the data. And when we are adding noise to the data, we have problems with the thermomechanical consistency. But it's normal because, I mean, now the data is not perfect. I mean, here the data is synthetic. I mean, we generated the data from the phenomenological law. That is why the behavior is quite good actually. But when we have noisy data, we have some other problems like a thermomechanical consistency. But we are not imposing more than that. It's only balance equation that we are satisfying that. We are enforcing to satisfy the balance equation. We are enforcing to satisfy compatibility equations and nothing else.
Okay, thank you. We can talk later.
Yeah.
Anyone else? Okay, let's thank Bruno again. Thank you, Bruno. Very good. Just a few things. Let me just put here. Paulinho, can you project the computer, please? Computador aqui. Aí, obrigado. Guys, just to let you know that we have here the form for the dinner, right? If you want to attend to the dinner, please fill in this form. We have to register, of course, to do that. And there is information about the restaurant and also the menu for the restaurant. Please do that. We will consider the first 40 registration because the place has only 40 seats, all right? And a very important person in the audience asked me to advertise this this roundtable that is going to be on Wednesday morning here in this same auditorium. So everybody is invited. It's organized by Poti, of course. And there is a, oh, this is the web page. Yeah, we'll have nice talks by Sean McKee, also Michael Vinicki, Poti is going to talk as well, Cássio, and Santiago. So this is the program, and it's going to happen only on the morning. So everybody's invited. Please come to see this very nice event. Okay, so we're going to go out for lunch right now. If you guys want to join, perhaps we're going to go to the El Cardal, but you are free to go wherever you want. All right, thank you.